Hey guys, okay, so we are going to move on here to 3.2. I'm just going to do some separate notes here first, but we're going to talk about implicit differentiation. Okay, and again, differentiation is the act of taking the derivative. Okay, and so we're going to talk about explicit versus implicit. Okay, and so we're used to this one. And what does this mean, explicit? So a function that is solved explicitly for y would be like that, right? This is solved explicitly for y. Okay. Implicit is different because if you had the same exact equation written as negative 2x plus y equals 1, we know that these things are the same, but we're going to learn how to take the derivative of this guy that's not solved for y. Okay, and sometimes you can't even solve for y. Here we would be able to just move it over and take the derivative. But what we're talking about is we know how to take the derivative of this function with respect to x's, but how do we do it here when it's not? Okay, all right, so I'm going to come into the notes here and we'll talk a little bit about how this works. So again, just notation wise, this d says take the derivative, okay, of this function with respect to x. Here's the problem, okay? This letter is y. And so when you're taking the derivative with respect to x of a letter, right, that doesn't match this denominator, x value, you have to do the normal power rule, okay? And so the normal power rule is to bring the n down, multiply by 1, y to 1 smaller, so n minus 1. But you have to add in this statement here, which is the derivative of y with respect to x. This will be weird at first, but it gets much easier. Okay, so this says take the derivative of y with respect to x, but y doesn't match x. So what we're going to do is we're going to take the derivative of y, so we'll bring down 1. We'll multiply by y to the 1 smaller, which is the power of 0. But because y doesn't match x, the derivative that we're taking with respect to, we would add in dy dx. 1, that becomes 1, so this is just dy dx. Okay, what happens if you take the derivative of y squared? Power rule says 2y to the power of 1, but because y doesn't match x, I need to put in dy dx for a final answer of just 2y dy dx. And so on and so forth. This would be 3y squared times dy dx because y doesn't match x. Okay? Now, that might seem really weird, and that's very normal every time I teach this, right? This is very odd at the beginning, and then it gets really easy. But let me explain to you that you guys have already been doing this. So if I gave you y equals 4x squared plus 2x plus 1, let's take the derivative with respect to x of this whole thing. Okay, so we just did this. Let's take the derivative of y with respect to x. Well, we get 1, and then y doesn't match x, so we write dy dx. And then over here, we're taking the derivative with respect to x. So these guys match, okay? And so this would just be 8x like normal. And then theoretically, you could put dx dx, but that just goes away because it's 1. Same thing here. The derivative of this term with respect to x, that is an x term, so this just becomes 2. I could put dx dx, but again, I don't because it just would reduce to 1, giving me a final answer of dy dx equals 8x plus 2. And we've been doing this whole time, right? I told you guys that dy dx is notation for the derivative of y. Now, hopefully you understand why that dy dx is there, because the y doesn't match the x. And so we just use our normal power rule, but then we have to add that term in. Okay, so let's see it in motion here on an actual function. So you can't solve this explicitly for y. Okay, 3x squared plus 4y squared, 3x squared plus 4y squared equals 2x. If I asked you guys to solve this for y, you would have a really hard time doing it, right? You could isolate it, and then you could divide by 4. Okay, but then eventually, you guys, look what you're going to have to do. You're going to have to square root both sides, giving you this plus or minus, right? Which is really, really hard to work with. This is actually two functions, so you can't even solve this equation for y. So if we could just use all the rules we've learned. But because we can't, you have to take the derivative. We're going to take the derivative of this whole thing with respect to x. 3x squared plus 4y squared equals 2x. So this is saying take the derivative of this whole equation with respect to x. So when you do it of this first term, like we talked about, this is an x term. And so we just use our normal power rule. 2 times 3 is 6, x to 1 smaller. But here, when we take the derivative with respect to x, the y doesn't match the dx part. And so we still do our power rule. 2 times 4 is 8 times y to 1 smaller, but I have to add in dy dx because that doesn't match that. Okay, hopefully it's starting to get a little easier. We take the derivative of this term with respect to x. These are x terms, so the power rule simply says that. Okay, and the rest is just algebra. If I'm trying to find a dy dx, there it is, right? Just get it by itself. So we have 8y dy dx equals 2. Remember, we need to subtract 6x. And then we're going to divide by 8y. And so dy dx is going to be 2 minus 6x, all divided by 8y. Okay, and that is your answer, which looks very different to you guys, right? Now you have a derivative that has both an x and a y in it, but that's okay. It's all normal. Okay, and so now that we have this skill set, right, implicit differentiation, we can do the same things that we've always done, right? Find tangent lines. I told you guys this isn't going to go away. What do you need for a tangent line? You need a point and you need the derivative, right? dy dx at that point, 1/2 negative 1/4. You guys will notice that my words didn't change, but look at my notation. So I need a point, I've got it. I also need the derivative of y with respect to x. This line right here means evaluated at that point, okay? Before, remember how we just did at the x value? Well, look at our derivatives now. Now we might have an x and a y in it, and so I have to use both pieces of the point. But my definition of a tangent line did not change. Point and derivative at the point. Okay, so let's do it. Well, you'll notice that this equation is exactly that equation from before. So we can go right down here and say, well, I know dy dx is equal to 2 minus 6x over 8y. Okay, I'm going to introduce some notation here. I'm going to use this bar line. So I'm going to say evaluate that at 1/2 negative 1/4. What does that mean? That just means to plug the point in. So I get 2 minus 6 times 1/2 divided by 8 times negative 1/4. Okay, so that becomes 2 minus 1/2 of 6 is 3. And 1/4 of 8 is going to be 2, but negative. And so I get negative 1 over negative 2, which is positive 1/2. Okay, cool. So we've got our 1/2. We've got our point and our slope, and so our tangent line would simply be the y value, negative 1/4, plus my slope, which is positive, times x minus my x value. And that is the tangent line. Okay. All right, so some of you from pre-calculus, maybe you remember, if you have x squared and y squared, this is most likely going to be, it is going to be an ellipse, right? If you set this equal to 0 and you did all that fancy stuff from before, now you have this ellipse, okay? So maybe it looks something like that, I'm not sure. But at that point, right, 1/2 negative 1/4, you found this tangent line, which maybe it's right there. Okay, so all we're doing is finding tangent lines of different looking functions. Okay, let's keep practicing here. So on the next page, we're going to find, again, a tangent line. What do we need? We need a point. We've got it. And we need dy dx evaluated at that point 0, 0. Okay, really important to understand notation so that it doesn't scare you. Okay, so all we need to find is the derivative. All right, well, look. We are going to take the derivative with respect to x of this entire thing, which is e to the y cosine of x equals x plus 1. And now we have this new ability to take derivatives implicitly, meaning I don't have to solve for y. So I can just straight up just go, take the derivative. This is a function. This is a function being multiplied together. So we're going to use the product rule. And so we're going to say first, which is e to the y, times the derivative of the second, which is negative sine, plus the second, which is cosine of x, times the derivative of the first, which is e to the y, equals. So we took the derivative of that, and it's the product rule. Now let's take the derivative of x. Well, the derivative of x with respect to x, these guys match, okay? And so we got to go back and fix this, right? First derivative of second, derivative of this guy was an x, so that's okay. But then we did second times the derivative of the first, but that guy has a y, and so we need dy dx right there. Okay. Now when I do the derivative over here of just x, because they match, that would just be 1. And the derivative of 1 is still considered a value of 0. So let me reiterate. Product rule first, you just rewrite it. No dy dx because we didn't take the derivative. Times the derivative of the second, which is a function of x, so I don't need a dx dx, it just would go away. Plus the second function times the derivative of the first, but the derivative of first is a y that doesn't match x, and so that's why I put in the dy dx. Okay? All right, so let's just go ahead and do this. You guys, we need to plug in 0, 0. So a big line, I'm going to say, look, I'm going to evaluate that at 0, 0, which gives me e to the 0 times negative sine of 0 plus cosine of 0, e to the 0, dy dx equals 1. Okay, sine of 0 is 0, so this whole thing goes away. Cosine of 0 is 1. E to the 0 is 1. Dy dx equals 1. And so I have that my derivative at 0, 0 is equal to 1. Tangent line is equal to the y value, which was 0, plus the slope, which is 1, times x minus 0. So if you just clean that up, that goes away. You just get 1x, or y equals x is your tangent line. Okay, and you guys don't even know what this looks like, right? This is a function that has a random y in it and an x. And so even though we don't know what this looks like, we know that the equation of a tangent line there is just x. Okay, so straight up tells you to use implicit, and it wants you to find the first derivative and the second derivative, okay? And so let's go through the first derivative. So I'm going to rewrite notation. The derivative of this function, y squared minus x squared equals 5, with respect to x. Okay, so here we go. Term by term, that becomes 2y. Y doesn't match x, so I need a dy dx. Minus, that's an x term, so that just becomes 2x. And the derivative of 5 is 0. Okay, solving for that, you would get 2y dy dx equals, if I add it to this side, I get positive 2x. For a final answer of dy dx is equal to, when I divide by 2y, I just get x over y. Okay, so we are supposed to find the first and the second derivative. So this guy is done. That's the first derivative. Okay, so how do I find the second derivative? Notation here, I'm going to write d 2y dx squared. So that is the same as this. This reads the second derivative of y with respect to x again. Okay, so all the 2's mean is that it's the second derivative. Okay, so let's do it. Here's our first derivative. We know to get the next derivative, you have to take the derivative of this guy. So quotient rule says low, which is y. I didn't take the derivative of it, so there's no dy dx. It's just the low times the derivative of the top, which is 1. Low d high minus high, which is x. D low. Well, the derivative of y is 1, but y doesn't match, so I need dy dx. Low d high minus high d low all over low squared. Okay, now technically we're done here, except on the AP exam and in this problem it says, look, I want y double prime in terms of x and y. I don't want this. Okay, and so remember, this guy right here is equal to x over y. And so we can simplify this and say this is y minus x times dy dx is x over y all over y squared. Now I've got the second derivative in terms of just x's and y's. And so I'll keep simplifying. This will become y minus x squared over y all over y squared. And then we'd have to get a common denominator up here to simplify. Okay, and then as we rewrite this, we get y squared minus x squared all over y squared. Okay, and then you've got to figure this out, right? This is this divided by that, or 1 times 1 over it, for a final answer of y squared minus x squared all over y cubed. Okay. Okay, so this is definitely notes. I think that if we were in a classroom setting, you guys would have some more questions. I'd be going around and helping. So what you want to do is you probably want to rewatch, right? You want to maybe rewrite these somewhere else and practice and see if you can come up with these two derivatives. But at the end of the day, what we're doing is we are still taking derivatives of entire functions that can't be solved for y. And so I can do that term by term as long as I pay attention to what the term is. And if the letter of the term you're taking the derivative of doesn't match the denominator value of x here, that's why we add in the dy dx after we take the derivative. Okay, again, you'll be watching this on Tuesday, so periods 1 and 3, we'll be doing a lot of this together, and then period 5, I'll make sure and do a lot of these questions with you on Wednesday. Okay, take care, guys.